Hi everyone, I'm Mohammad Sayeb. I'm a graduate student at the University of Florida working with Dr. Blecha on massive black hole binary evolution. Today I'll be talking about binary evolution, Inspiral, and spin evolution with precession in a cosmological framework. So this study of these systems from a big picture perspective will help us understand problems such as M-sigma relation and galaxy black hole coevolution. But today I'll start things off by talking about the population of black holes that we consider, which are from Illustris cosmological hydrodynamics simulation, and I'll describe the models we have for the evolution of these systems below the Illustris resolution, and I'll also talk about the spin evolution of this system and how they connect to the recoil velocities and what they mean for the recoil velocities. And last but not least, I'll mention the strongly precessing systems in the LISA waveband. So to start things off, the population of black holes that we have are from Illustris cosmological hydrodynamic simulation, which is basically a simulation of the universe. But in the Illustris simulation, due to computational efficiency, when two black holes get within a softening length of each other, they are spontaneously merged. However, these softening lengths could be of the order of a few tens of kiloparsecs to a few kiloparsecs, and a lot of things could happen to the binary below that separation. So the idea, we modeled those the evolution beyond these separations and see what happens to the black hole. So one of the first things that can happen is the dynamical effect of the dynamical friction, where the binary moving through a uniform background creates these overdensities that exerts a gravitational force on the binary and causes the black holes to lose energy and move further to the center of the potential. And from a few hundred parsec to a few tenth of a parsec, we have the effects of stellar scattering being dominant. In this regime, the binary starts interacting with individual stars, and the requirement for the momentum of a star in order to interact with the binary in the phase space is represented by a cone. So we also name this stage of evolution as loss cone. And beyond that, we have circumbinary disk that is formed, and binary loses momentum momentum to the disk, and that's how it loses energy. And last but not least, from a few milliparsec down to the point where the binary merges, we have gravitational wave, emission of gravitational wave that is the dominant factor in the shrinking of the binary separation. So in the disk phase, which is a gas-driven phase, the torques, so we will have a circumbinary disk, and then the torques from the binary also creates this gap that you can see over here, and each of the black holes, the primary, which is the more massive black hole, and the secondary, which is the less massive black hole, will have their own accretion disk. But the amount of accretion onto each black hole is a strong function of the mass ratio. On the right plot, you see there have been a lot of studies done on this, and on the right plot you can see that as mass, we have used this fits to Ferris et al. Data 2014a, and you can see as the mass ratio increases and gets closer to 1, the accretion onto black holes becomes more balanced, so it gets closer to 1. A y-axis shows the accretion rate ratio. But as the mass ratio decreases up to 10 to the power minus 1 or 0.1, we see that the accretion ratio of the secondary over the primary keeps increasing, which makes sense again, because the more massive black hole will stay closer to the center of mass, and the less massive black hole will be moving around a lot more, and it can accrete more, which as a result will curb the accretion by the primary. But then for smaller mass ratios, the accretion onto the secondary will not be enough to curb the accretion onto the primary, so we see that the ratio keeps decreasing, meaning that the accretion rate of the primary keeps increasing. Now, the idea here is, the reason why we look at the accretion rates is because they determine how long it takes for the spin of the black hole to align with the circumbinary disk. More accretion means more efficient alignment, and less accretion means less efficient alignment. So using those ideas, we can see that here I have plotted the Inspiral versus alignment timescale for the primaries and secondaries. And the basic idea of differential accretion was that up to some mass ratios we have secondaries accreting more and the primaries accretion getting curbed, and then due to a less efficient accretion, the spin alignment timescale will increase for primary, right? So that's what we are seeing here. The blue primaries are shown in blue and secondaries are shown in red. We can see that there are more primaries with alignment timescales larger than the Inspiral timescale, meaning that by the time the Inspiral comes to an end, the spin of the primary hasn't aligned properly, so it's misaligned. And this is true for some of the secondaries too, and all the values below the diagonal line show these kind of systems where they stay misaligned by the end of Inspiral. And on the other side of the diagonal, we have systems that are aligned, meaning that their Inspiral timescale is longer than their alignment timescale. So they get aligned pretty much by the time that the Inspiral comes to an end. The arrows are systems that never got a gas-driven dominated phase, so their alignment timescales are very large. They're essentially misaligned by the end of Inspiral. So using this idea, we assign, so by the end of disk phase, we'll have to decide on the spin of each black hole. So for the aligned systems, for the ones that have an alignment time scale smaller than the Inspiral, which is the upper portion of the diagonal over here, we assign them an aligned distribution by the end of the disk phase. And for the other portion, the misaligned ones, we assign them an isotropic distribution, assign their spins an isotropic distribution. So theta here is the angle that the spin of each black hole makes with the orbital angular momentum. I'll show that in next slide, in 2 slides after this. And in terms of percentages, we have 19% misaligned primaries and 10% misaligned secondaries. And as we see from the effects of differential accretion, we have more primaries that are misaligned. Now, after we have that distribution of spins at the end of disk phase, which is the beginning of the gravitational wave-dominated phase, we use those as an input or initial condition for our gravitational wave-dominated phase. In the gravitational wave-dominated phase, spin precession happens. The spin starts precessing, and this effect is important because the spin orientations right before merger tend to have a strong effect on the recoil velocities, and the more misaligned the system is, the higher the recoil velocities are going to be. And spin precession basically determines the configuration of spins right before the binaries merge. There have been many studies done on this. In case we have black holes binaries that don't spin, the maximum amount of recoil velocity we can get is 175 kilometers per second. But for a spinning system that spins partially aligned with the orbital angular momentum, we could get recoil velocities of up to 5,000 kilometers per second, which is very significant. And so some of these high velocities means that we could have black holes that could get completely ejected from their host, or even for smaller ones, we could get massive black holes that can be temporarily displaced from galactic nuclei. So in order to have everybody on the same page, the sketch over here at the top shows the different parameters that we're dealing with in the spin precession. The theta 1 is the angle that the spin of the primary makes with the orbital angular momentum, and theta 2 is the angle that the spin of the secondary makes with the orbital angular momentum. And if we consider the projection of these two spins onto the orbital angular momentum, the angle between them is called delta phi. Now these are the angles that evolve during the spin precession. For angle theta, over here on the left we see the initial and final final angles for primary and secondary. For the primary, initial meaning when gravitational wave dominated phase starts, and final is when the binaries merge. So we see that for primary there is not much of a change occurring, but for the secondary it gets more misaligned as the binary gets closer to the merger. General effect is that cosine of the polar angle of the primary becomes equal to cosine of the secondary's polar angle. And for the other angle, the evolution of delta phi, an effect called resonance effect occurs, where the delta phi angle gets locked either around 0 or plus minus pi, and in our case it was plus minus pi, and it's because we have a large population of systems that have a small mass ratio, and that biases this resonance effect towards plus minus pi. But this delta phi orientation has a strong effect on the recoil velocities, where if we consider two populations, one with precession and one without precession, the recoil velocity could change by up to 1,000 kilometers per second. But surprisingly, this does not have a strong effect on the distribution of the recoil velocity for the specific population that we are looking at. And the more determinant parameter for this is the polar angle theta I, or the polar angle of the black holes. So this shows a plot of the recoil velocities, and as I mentioned earlier, so if we look here, I'm not going to talk about all of these curves here, but what we have tried to do here is we try to have look at the extreme cases for the spin alignment or misalignment and see what happens. The dotted line shows a population that's fully aligned, and the dashed dotted shows a population that's fully misaligned. And we see that for the fully aligned, the recoil velocities are smaller, or the smallest of all the models that we have studied, and for the isotropic model, the recoil velocities are the highest, and the fiducial model lies somewhere in between, because the spins were extracted from a combination of those two distributions. So this is something that we were expecting. Now, last but not least, we have seen that there are a significant number of systems that experience strong precession. This is discussed in more detail in the paper, so you can read that, but we see 14% of all the merging binaries have a precession amplitude of larger than pi over 6. Precession amplitude is denoted by theta L over here. This is the angle that the orbital angular momentum and the total angular momentum make with each other. And there are 5% of systems, merging binaries, that have a precession amplitude of larger than pi over 2. And we can also see this effect that as the separation decreases, the precession amplitude increases. So what this means is that there could be a significant number of strongly precessing binaries that could fall within the LISA waveband, and they could be detectable by LISA. So please check the paper for more details. And here is the summary of the main points that I discussed today. Please feel free to ask any questions that